Hello, AP Calculus AB. We are back to a new unit and we are ready for some fun. We actually only have 2 units of study left before the AP exam, and both of them are shorter, thankfully, than the last one. This unit or topic is another two-parter. And so you can see our title up at the top is Topic 6, Applications of Integration and Differential Equations. Now, I go in a slightly different order than your textbook will go. Your textbook has a chapter of applications of integration, and I actually only do about half of it here, and then I make the last bit an entirely different unit. Applications of integration are exactly what it sounds like. Basically, you know all the important integration tools. Now, how can we apply them to actual real-world problems? As a reminder, our College Board talks about having you gnaw on AP-style problems, and we've done really 3 of these pretty well, where the G is you approach something from a graphical perspective, the N is numerical, and when you hear about numerical data, it's usually data displayed in a table. A you can hear of as algebraically or sometimes analytically, but either way it's information displayed in an equation. But the W we really didn't touch on much in Unit 5, and that is going to be a big deal for this unit. The W, of course, stands for written, or sometimes you hear it for a real-world problem. So what we're going to do is we'll see data presented graphically, numerically, or algebraically, but from a written contextual perspective. So they're going to say, here's this data, but here's what it means. And now you do all your cool calculus stuff, but after you get your answer, make sure you tell us what your answer means. So there's going to be a lot more interpreting here. But on the nice side of things, you aren't learning really any new techniques. Because, though, we are using real-world data, we will find that you'll want a graphing calculator pretty much every class for this unit because real-world data is pretty gross, and I wouldn't want to be doing those calculations by hand. So we're going to learn a few tricks with the calculator. You'll use it pretty much every class. But finishing that rundown, what are we doing for applications of integration? Realistically, because we already know all the skills, we're just going to see a couple specifics of how to apply those skills. And we're going to do that mainly through practicing different styles of free response questions. Today is kind of an offshoot, though. Today we need to talk a bunch about units. You might recall we did a lesson on this when we did everyone's favorite related rates. Oh, that took me forever to get to. And so we're going to do something again, but don't worry, this unit is not nearly as bad as related rates, I promise. Either way, that's the first half of this unit. The second half is called, or abbreviated to, DiffEQ, and is all about differential equations. And your textbook, and many teachers, I think, split that into its own unit, but it's only 3 days of lessons, and that's kind of a really weird, tiny unit, so I just rolled into this one, even though they're not super related. So let's get to it. Day 80, Riemann sums and units of integration. There is a quick opener here. They're asking you about the equation d equals r times t. Now, sometimes my students have seen that equation before, and other times they have not. So let's see if you can identify what each or any of those variables mean. I bet you can guess, especially for t. And then see if you can create an example using units in which d equals rt applies. Ready, set, go. All right, so you may have known that D in this case usually stands for distance, R stands for a rate, and T almost always stands for time. We're going to be using that variable T quite often here. What are some potential units for each? Well, time is easy, right? We can have seconds, we can have minutes, we can have hours. Distance is pretty easy, right? You can have miles, you can have kilometers, centimeters, anything like that. Rates can be a little trickier until you remember that rates are like speeds. So maybe something like miles per second, or kilometers per minute, or centimeters per hour, something like that. They did ask you to create an example using units, and so I'll just do a very quick one. All right, so let's say that I talk at a rate of, let's say 30 words per minute, and I talk for a time of 6 minutes. So if we apply this D equals R times T, 30 words. I'm going to zoom in. You might recall that I always write my units like straight fractions. I think it's easier to see what cancels here. Times 6 minutes. And so we find that the minutes reduce. 6 times 30 is 180, and we're just left with words. Now, especially based on this example, even though the formula D equals R times T is more common, I definitely argue that distance, or the variable D, is a pretty poor variable because it's a little too confining. In fact, on my example up here, I got a distance of 180 words, and that doesn't mean, I think, what we were intending it to mean. Instead, I like the formula A equals R times T, where A stands for the amount of something. So in this case, if this was A up here, then the amount, or the number of words that I speak after 6 minutes, is 180 words, and that makes more sense. All right, now to understand the connection between units and integration, we're going to go through 4 fairly silly examples. And just humor me for a bit. I think you guys will understand where it's going after maybe the second or third example. So let's run through it. We have a printer, and I think pretty much everybody hates printers. Like, that's one of the few things we can come together and say, we don't like you. Either it's a color printer and you run out of cyan and now you suddenly can't print anything, or it's an ISO printer and it jams every time, or, either way, printers are just fairly terrible. You think they would make them better. And it's funny because I've read articles on this, and I know this is a side note, and they're like, printers are way better and they're actually pretty spectacular. Cool. I would like them to be more spectacular, please. All right, here we go. A printer can print pages, excellent, good so far, at a rate of 10 pages per minute. It prints for 3 minutes. Your goal is to create 2 different graphs to model this situation, and then explain how you can use each graph to find the total number of pages printed. Now, as some hints here, because my students are great at figuring out the first graph. Unfortunately, that's not really the point of today, this first graph, but it is an applicable graph, so it's probably worth doing. So one graph is going to relate time along the x-axis. Time is almost always our independent variable, to the number of pages printed. And really, I should do PPP because we use PP for pages and then P for printed. But either way, we can think of PP as pages printed. And then the other graph is going to go through and relate time, there we go, to the rate at which pages are being printed. The rate pages are printed. Okay. So I'd like you to play around with that for a quick second, and then we will come back together. Ready, set, go. All right. Well, I bet you kind of did some math in your head for this first graph, and you said, well, we're printing for 3 minutes. 1, 2, here's 3 minutes, right? It's the time in minutes, can't hurt. And then you just started graphing, and here's where you did math in your head. You said, okay, if it's printed for 1 minute, then that means it's printed 10 pages. 2 minutes, it is printed 20 pages. And 3 minutes, it is printed 30 pages. And then you connected these. Hopefully you drew some points a little bit better than I did. Awkward. There we go. Slightly better. Good. Cool. There's a big gap there, but oh well. Great. And you said, well, how do we use this graph to determine the number of pages printed? You look at the input of 3. You look up here, look over. Bam. We found it. It's 30. The input correlated to an output of 30. We crushed it. There were 30 pages printed. All right. Let's take a look at this one. This one had a time, so it seems like 3 minutes makes sense. 1, 2, 3. And then we printed at a rate. Well, actually, I don't think our rate changed here. Wasn't our rate at 10 pages per minute the entire time? And so I think if you graphed the rate here, then at 1 minute, we're printing at 10 pages per minute. 2 minutes, 10 pages per minute. 2.5 minutes, 10 pages. 3, 10 pages. We're just going over here forever, aren't we? All right, well, how do we determine the number of pages printed? We know it has to be 30, so how do we turn this graph into 30? Well, it should probably make sense. It's going to stop at 3, so we might as well put a little boundary there. It's also going to stop at 0. Can you see any math that will give us an answer of 30? Well, maybe you're looking at this and you're saying, well, isn't this x-axis down here this guy, this has a length of 3, doesn't it? And because it's time, doesn't it have a length of 3 minutes? Kind of weird to think of time as a length, but it'll work. And then what about its height? Well, I think its height rate here is 10, and we're going to include the units pages per minute, right? And how do we get 30 out of that? Well, couldn't we just multiply those two together right here? Couldn't we take this 3 minutes and multiply it times 10 pages per minute? And as we saw on that A equals R times T, if we multiply these together, the minutes cancel, and it leaves us with 30 pages. Look at that. That was exciting. Now, why is this relevant? Well, what did we just find here? Didn't we just find the area beneath a curve? Isn't that exciting? Look at that. We just did some area stuff. We actually just did an integral without really knowing it. And we found our area. And we multiplied the units of the x-axis times the unit of the y. And it gave us our correct units. How cool. All right, well, let's look at a second example. We now have a printer that can print pages at a rate of 10 pages per minute. Well, that's exciting. We've done that before. It also prints for 3 minutes. Cool. This seems done already. However, over the first minute, as the printer warms up, it only prints at 5 pages per minute. Let's see if we can create a graph of this friendly old scenario here. We are going from 0 to 1, 2, and 3, something like that. All right, and its rate is going to be on the y-axis, and this is going to be time on my x-axis in minutes. Rate, we have 10. Oh, wait, we should do better than that, huh? Let's put 10 way up here, 10 pages per minute. Then down here we have 5 pages per minute. That makes sense? Okay, we know for the first minute it prints at 5 pages per minute. Sometimes I see students do this, but that wouldn't be right. That would mean at like, I don't know, half a minute it's printing at 2.5 pages per minute, and at, oh, I don't know, at a quarter of a minute it's only printing at, like 1 page per minute, so on and so forth. It says it prints at 5 pages per minute. So doesn't that mean until it hits 1, it prints at 5 pages per minute, and then once it hits 1 minute, it's going to jump up, and now it prints at 10 pages per minute. There we go, graphing these rates right here. Exciting. How do we find the total number of pages printed? Well, I think it's very similar to what we did before. We're going to go ahead and kind of block this off and block this off over here, and I think we have 2 rectangles here. And if you wanted to show the math, I'm going to do the math over here. We'd have the green rectangle, which has a base of 1 minute, again kind of weird, and a height of 5 pages per minute, like so. And so to find the area, it would be 5 pages per minute times 1 minute. And then we add on the second rectangle, which is this guy over here. I guess I can shade this one in. This one, of course, has a base of 2 and a height of 10 pages per minute. Very weird to think of heights in terms of rates, but that is what we're doing here. And as we go through and work this problem out, I think our minutes cancel, We're left with 5 pages times 1, which is just 5 pages. Plus, and then we have 10 pages times 2, which is 20 pages. And if we add them together, we get 25 pages. Look at that. Very exciting. As you're going through here, right, we got these 25 pages. We should ask ourselves, does that make sense? Well, earlier when we printed at a constant 10 pages per minute for all 3 minutes, we got 30 pages. Now we're not doing a constant 10 pages per minute. We're only doing that for the last 2 minutes. We're using a slower rate for this first minute, so it should make sense that we have slightly fewer pages. Good for us. All right. Now our printer prints continuously, but its output is the time of day rounded down to the next lowest hour. So when it's printing at 9:05, it's printing at 9 pages per minute, and so on and so forth. How could you find the total number of pages printed after 24 hours? Let's say we're printing out, Wikipedia or something like that, right? There's enough pages to last us 24 hours. The question I always get asked on this when students start to build their graph or their axes is they say, wait, are we using military time or are we using standard time? And my answer to you is, I don't care. Whichever one you'd like to do. You're going to get 2 different answers, but it's the same experiment either way, so go wild. Ready, set, go. All right. Let's go ahead and look at time. I think you'll find that it's probably easier to use military time, and I'll remind you how that works, right? Military time starts at 0000, and that is essentially midnight. And then as you count up, as you get to our first hour over here, right, a 100, and then we continue up, and you can, you have more things going on over here. You have, let's say, noon, and then we continue adding afternoon. So we're going to say we end over here at 2400. That would be essentially 0000. That would click over, which is fine. So there's other numbers in here, right? 1600. And to convert between military time and the standard time we're used to, we would just take 1600. We subtract 12 from it, and that tells us that that is 4 in the afternoon, right? So this is 4 in the afternoon. You subtract 12 from here, it's midnight, so on and so forth. Either way. All right, now let's look at our rate, because this is where things get wild. Well, from 0 just up until 1, so from 0 up to, let's say, 59 minutes into the day, it rounds down to the nearest hour. So that means if we round down to the nearest hour here is 0. So from 0 to a 100, it is printing at a rate of 0. Okay, and then from 0100 to, I should probably put this one on here over well, there we go, to 2 a.m., right? So some sample times in here might be something like 1:32. We always round down to the nearest hour, and so that's printing at a rate of 1 page per minute. What I think this actually means is that on this last time from 2300 to 2400, it's printing at a rate of 23. I need to go all the way up to 23 here. Now, there's no way I'm going to fit all these, but I'll do my best. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and skip a few, 99, 23. Awesome. Okay, so this is 12 right here, just so we can get an idea of what this graph looks like. Right? It's going to skip up here and print at a rate of 1, and then from 2 to 3 it prints at a rate of 2, and so on and so forth. You may have seen this function before. You can call it a piecewise function. You'd be right. There's multiple pieces here. Yeah. Some other people will call this a step function because, shockingly, it looks like a set of steps, and so on and so forth. And the question here becomes, how could you find the total number of pages printed after 24 hours? And the answer is, you make a whole bunch of rectangles. For example, this rectangle right here, you find the base, you find the height, and you multiply them together. The units cancel, and it will give you how much was printed along that time. And you could actually come up with a function to do this too if you really wanted, but that's not the point of today's lesson. The point of today's lesson is how, if we are given a graph of a rate and a time, can we use that to find an amount of stuff? And it all comes back to the A equals R times T. So let's look at one more and then get our conclusion in. Now our printer decides to be really weird. And maybe those of you with older printers won't even think that this is weird. You're like, no, this actually makes sense. So now its rate is based on how much is actually on the page. Let's say the amount of data or the amount of space that the page is taking up if you were to save it to your hard drive. So of course, if it's a page with a picture with a ton of pixels and it takes up a ton of space, let's say our page takes up 15 megabytes versus a page with just text that takes up like 2 kilobytes, they're going to print at different speeds. And what's going to happen is, let's say that we have this rate that's oscillating up and down, and we have some time over here, okay? And the question becomes, what is our graph going to look like if we try to print out the entirety of Wikipedia? Well, I think it's going to be all over the place, right? You're going to get to a page on Wikipedia, and it's going to be super fast, right? A high rate up here because it's really low. Then it's going to drop down. It's going to do something over here and going to print here and probably not jump back on itself, and so on and so forth. And the question becomes, how do we find the total number of pages? Well, you go through and you subdivide this into as many rectangles as you can. In fact, with these rectangles, we should probably start thinking of the base as dt. and the height as, well wait, this is a rate. How do we describe rates in calculus? Oh, couldn't we call the rate like f prime of t? Isn't that a rate, right? A derivative of a function. So maybe the height is f prime of t. And if we wanted to find the area, which will give us the units or the amount of one rectangle, it would be f prime of t, the y value, times dt, the infinitely small x value here, right? Which would give us that perfect area. But then wouldn't we want to sum all of these up? And if we're going to sum up using dt, then wouldn't our amount actually be given as, let's say, from, oh, I don't know, how about we just go from a to b over here? Wouldn't this go from a to b of f prime of t dt? And yeah, we're back to calculus. So, to find the area of example 4, we use our current method of study, integration. Okay. We would set it up like this. The integral, so the amount, equals the integral from first time to a second time of f of t dt. Now, sometimes you'll see f of t. I used f prime over here, and it all depends on what they call their original function. A lot of times they try to be crafty, and they'll call the original function f of t. Okay, and so maybe we could even think of it as down here, like this is f of t or something, right? And then in their integral, they'll use lowercase f. But as we've learned before, that's the same relationship as f of t to f prime of t, right? Versus capital F to lowercase. And why might they prefer this notation over this one? It's because the bottom notation that's circled takes up less space. Seriously. This apostrophe or this prime symbol adds an extra space. Why add an extra space when you can do not add an extra space? So either way, same thing as we go through. F of t represents the output of our graph, which has units of, and I think in this case it was pages per minute. The bases of each infinitely small rectangle have units of time, or in this case minutes, we'll probably say, and are represented by dt. When we find the area of each rectangle, the units multiply, right? We see pages per minute times, oh, wait, I should read my own writing first. They multiply as, struggling here, as minutes, we'll do the first one, times pages per minute. And so those will cancel and give us a final unit of pages. Then, of course, we sum up all the rectangles, which is why we use an integral symbol, which is just a fancy sigma or s, if you will. Notice, too, that f of t was a rate. In fact, you could also call it f prime of t, where the integral gives us lowercase f. Okay, enough jargon. Let's put this into practice. An object is moving in one direction. Its speed in centimeters per second is decreasing along the interval and is recorded below. All right, so we see time in seconds, and we see f of t, which is in centimeters per second, going down here. So let's go ahead and form a right Riemann sum to approximate the area under the curve for t equals 0 to t equals 6. If you still struggle a bit to form a right Riemann sum, that's okay. You can always go through and sketch in a graph, and it doesn't have to be perfect, and the graph will really help you with that visual. And I will show the graph on the first one. The other times we do this, I will not. Once you've done that, give correct units for your answer and interpret your result in the context of the problem. Is our approximation an over or underestimate? Okay, so why don't you guys try this one, practice those right Riemann sums, and then we'll come back together shortly. Ready, set, go. All right, I did promise you a quick little graph, and this is going to be a gross, ugly graph, and that's fine. So we have 2, 4, 6. Our time is in seconds. And then we have our rate up here, f of t, which is in centimeters per second. Okay, and we have 4 numbers on here, right? We have 1, 2, 3, 4. We have 20.2, 26.3, 35.5, and zooming in a bit, 45. And we go through and we do this, 0, 45, and this makes sense that it's going down. They told us our speed is decreasing. 2, 35.5, this guy, and then this one. Great. There we go. Form a right Riemann sum to approximate the area under the curve. Now, I think it's very, very important that you always set this up with an integral. It's going to help you with your units. So, we are going to find an integral. They asked us to go from 0 to 6, and we are doing the function f of t times, and this is where the times gets really important. Now I know most people don't put the times in between, but I think it helps make sense of the units. Times dt is approximated by, here's our right Riemann sum. Yeah, first interval is right here. A right Riemann sum means start on the right and draw over. Next one, start on the right, draw over, start on the right, and then draw over. Cool. And if you wanted to see that a little bit more clearly, you could use a dashed line to kind of show you where you drew over, but totally up to you. Great. We get 3 rectangles for 4 x values. And again, we could have done this without the graph. How would we do it? Well, we're doing a height, in this case, times a base, f of t times dt, and you can go the other order. The heights, though, are easy. There are 4 heights here, but because it's a right Riemann sum, we exclude the first one, and we're going to use the last one, the one that's on the right, even though it's at the bottom of the table. So my first height is 35.5 times something. My next height is 26.3 times something, and my last height is 20.2 times something. Times what? Well, I just took care of all of those heights, 1, 2, 3 heights, so the something they're multiplying by has got to be the bases. Visually, we can see all the bases are 2. How could we get that out of here? Well, we just look at the first interval from 0 to 2 and say, how long is that interval? That's an interval of 2. Look at the next subinterval, that's an interval of 2. Look at the last one, that's also an interval of 2. Okay. Now, continuing this out, and I'm going to use the space down below, we could also say that because 2 is in common to all these, we could factor out the 2, but even further, 2 has units. It has units of seconds. And I think seconds is more commonly abbreviated with an S, but I put SEC, which isn't secant, so I probably shouldn't do that. Either way, 2 seconds times, and then we should probably sum all of these up really quickly. If we sum these up, 5 and 5 makes 10, so it ends in a 0.0, and then this is 11, carry the 1, that's actually 12, and then 4 and 3 is 7, carry the 1 is 8. Okay, and what are the units here? These units are centimeters per second. And as we continue this out, this is going to be exactly equal. These seconds reduce. 2 times 82 is 164 centimeters. Now, did you have to show those intermediate unit calculations? No. In fact, this is why I like to do the integral. Because if you look at the integral that's here, right, we have f of t, where they already told us those units were in centimeters per second, right? We saw that over here. And then we're multiplying by dt, where dt is just a small interval on the t-axis, and t is given to us as seconds. And so if you set up your integral correctly, and you put in the units in the integral, you can see that these will cancel, and then we will sum up centimeters, so our answer better be in centimeters. Now, what did we just find? Because we had to interpret this result in context of the problem. Well, we found centimeters. That's kind of an amount, or actually I think it's even a distance here, isn't it? So what can we say? Well, I think we can say from t equals 0 to t equals 6, what do they say? They give us, it's an object. The object moves 164 centimeters, right? It's a distance, it's a movement. In fact, it becomes very useful, and I always do this with these problems because this is AP Calculus, which one of the main focuses of AP Calculus is the study of rates. Almost every single real-world problem that they give you will give you a rate. It'll give you a rate in a table, a rate in a graph, or a rate as an equation, a derivative, if you will. And so I always go through and I list the 3 levels, I consider them levels or rungs of a ladder if you want, of every problem. So they gave us a rate that's going to be in the middle. Think of a rate as like a first derivative, and this rate has units of centimeters per second. Well, if we work backwards, and to work backwards we have to, and I wrote an S, we have to integrate, right? Then that will give us units of centimeters. If we go the other way and we take the derivative with respect to t, what's going to happen here? Well, it's going to be how this rate changes as time changes. So you could totally treat this as centimeters per second per second. I actually like it that way, though you physics folks might call this centimeters per second squared. I always write this on every single real-world problem that gives units. It helps me so much to realize that as you take more derivatives, you get more units in the denominator, and as you take antiderivatives, you lose units in the denominator. All right. Now, is this an approximation, an over or underestimate? Well, I guess it depends on what the graph looks like, doesn't it? But luckily they told us that our speed is decreasing. F of t is a decreasing function. So how do I determine if it's an over or underestimate? I'm lazy, and I always just graph a decreasing positive function. And then I say, okay, let's split this up onto a couple of subintervals. We did a right Riemann sum, didn't we? Yeah, so here is my right Riemann sum. Oh, look, with a decreasing function, a right Riemann sum clearly under approximating. Look at all those extra gaps. So how do we write that? This is an underestimate because f of t is decreasing and we used a right Riemann sum. Ta-da! A bunch of information in one problem, but I just didn't want to take up the whole page doing little individual pieces. All right. Next, part B. Use the data to approximate f prime of 3 and then explain the meaning of this estimate. Now, this is one of the most commonly asked tabular or table questions, numerical if you want, where they say, okay, you have this first derivative. We want you to take the derivative of that at a certain point, but haha, we didn't give you 3 in the table, so what you gonna do now? Well, what we're going to do now is use a pretty poor, in my mind, application of the mean value theorem. So what does that mean? Pun intended. We're going to take f prime of 3 and we're going to say, well, if we want that, it would be great if we had an equation so we could take the derivative and just plug in 3. We don't, but the mean value theorem tells us if we pick two values, one smaller than 3, one bigger than 3, oh, look at these two, and we find their derivative. And actually, let's find that derivative first. Not the derivative, though, maybe the average rate of change, the slope of the secant line, right, the mean value theorem. Then we can use that to approximate f prime of 3, and we'll talk about why in just a second. So, approximated by f of 4 minus f of 2 divided by 4 minus 2. Or if we continue through, f of 4 was 26.3, f of 2 is 35.5, all of this divided by 2. And I really don't want to do that, so let's see, 26.3, 35.5, we'll do it on Desmos. So I have 26.3 minus 35.5, and then divide that by 2, so we have negative 9.2 divided by 2. Okay, negative 4.6. I probably could have done that math in my head. Oops, oh well. Negative 4.6. Nice. Now, what is this negative 4.6? Because I still argue it's not a great approximation of f prime of 3. Now, it could be the exact value of f prime of 3. But what we really did is we said we used 4 and 2. We start at 2, we end at 4. And all we guaranteed is that some time value between 2 and 4 could be 2.1, 2.2, 2.3, 2.4. Who knows? I mean, it doesn't matter one way or another. But the problem here is that they're saying, what's a good approximation for f prime of 3? And that could be a terrible approximation for f prime of 3. It doesn't have to be exactly in between. Again, it could be 2.01 gives the same derivative as negative 4.6. We don't know. But the AP exam loves this question. So how do you do it? Well, if they want you to approximate f prime of something from a table, you pick the two closest time values or input values to 3. Now, this could be 2 and 5. 3 does not have to be exactly in the middle, but you are required to pick the closest value lower than 3, that's 2, and the closest value higher than 3, in this case, that's 4. It's nice that 3 ends up in the middle, but that doesn't really matter. Again, it could have been 2 and 5, and they still would have had you use this approximation. But we're not done yet, because it says explain the meaning of this estimate. Now, one of the best ways to give meaning to an estimate is to use units. And units here are actually pretty easy because they give us units. They tell us whenever you do f of something, that's centimeters per second. And whenever you do t of something, that's seconds. We did f of something in the numerator, t of something in the denominator, and so to me, that's going to give us the units centimeters, or meters apparently, centimeters per second. And then the denominator, since we divided that out, technically there is a denominator here, it's 1. And so we would say per second. Now, what does that mean? Well, it means every 1 second that passes in time, we go down 4.6 centimeters per second. Or you could even relate that back to speed. You could say that for every 1 second that passes, the speed decreases by 4.6 centimeters per second. Or the really lazy way to do this, but is never wrong, is you use the word changes. And so I'm going to give you probably 2 or 3 different ways that you can interpret this estimate, probably from best to worst, I would say. So the best way, the most accurate way, is you could say so let's do it like this. F prime of 3 means at t equals 3, the speed, and we know it's speed because this is centimeters per second. You could also just call it velocity if you would like. The speed is decreasing. And actually, velocity would probably be better because speed and velocity can really be confusing here. Plus, velocity is really easy to abbreviate, is decreasing at a rate, and I know I'm using infinite paper, I apologize, of negative 4.6 centimeters per second. Now, that would actually be wrong. You're like, wait, you just made me write a giant sentence and it's wrong? It's almost right. Because you can't say something is decreasing at a negative rate, because that actually means the thing is increasing. So if you say decreasing, you have to realize that you intuitively interpreted this negative to mean decreasing, so you can't actually put the negative in there. You already accounted for the negative by using the word decreasing. So although that probably makes the most sense, the safest way to write this is f prime of 3 means at t equals 3, the velocity is changing. Just use the word changing, because changing can either mean increasing or decreasing, and then I always just write the value that we got. So we got the value of negative 4.6 centimeters per second. Oh, per second. I forgot the extra per second up here. Awkward. Okay, so that way you can just take whatever your answer is. You can always use the word changing instead of trying to rack your brain interpreting, saying, do I need a negative here, do I not? Just use changing, and then you're perfect. Okay. Nice. All right, part C. The function s of t equals that grossness could be used to produce values similar to the table up here. That's so cool. They're like, we didn't give you a function at first. Now we're giving you a function that isn't quite the same for the outputs here, but is pretty close. Now they want us to find the integral from 0 to 6 of s of t dt on our calculator and explain what our answer means. Be sure to give correct units. Again, if you give enough space underneath your integral, units are easy. Time is the same in this problem. Time is still going to be in seconds, right? And if it produces values similar to s of t, to f of t, then s of t will have the same units as well, centimeters per second. And so we can see that our final answer here is going to be in terms of centimeters. Now, I really like this problem because they asked us to do this on our calculator. And this is something we haven't done yet this semester. We haven't actually used our calculators to calculate an integral because we were just focusing on basic integrals that we could do by hand. And now that we're into these real world problems, we're going to start getting uglier functions like this that you can actually do this one by hand, but I don't want to. There's gross decimals, negatives, ew. So, calculator time. A few ways to do this, and I'll try to give you 2 for each calculator. We'll start with the Inspire. Okay, first way is you just go to home screen, and then I'm going to go to calculate, or I usually just hit the calculator button over here, and we're going to go to menu. Everything lives in menu on the Inspire, very nice. Calculus, and then you're going to pick integral, 3. All right, now you'll notice on my calculator that these limits of integration spots are grayed out. That's because mine is this CAS calculator up here. It does a little bit more, and I'll show you what that looks like in just a second too. But on most of your calculators, we're just going to go from 0, hit the up arrow twice, to 6, and then go back down and type in your function, right? 45, make sure you use this E button over here, not the one on your keyboard, 2 different E's. E to the power of negative 0.13, and then this is your choice. You can use X, you can use T, whatever sounds good. I'll use T here though, because everything's in terms of T, dt. Hit enter, and great. We got 187.475. You might be a little worried. You might say, oh no, wait, what, is that exact enough? Don't forget, you can go up, hit enter, and it'll go more out there. 187.474, or 0.475. 187.474 centimeters. All right, if we compare that up above, look at that. Aren't those pretty similar? I mean, yeah, they're off by 20 centimeters, but I mean, that's not too bad, right? So how do you explain what our answer means? Well, we use the exact same estimate, or the exact same interpretation of above, because it's doing the same thing, but in a different way. Now, I promised a couple different ways to do this, and so let's go through the rest. The second way that we could do this, let me clear this out of here, is you could go to your graphing screen first, and you could go ahead and type in that equation, though using x, because it's always a function of x. So if you already have that equation graphed, then I can just use the name f1 of x. That's what it's called. So back over here, I can do the integral from 0 to 6 of, and then instead of typing the function, since we've already typed it once, f1 turns bold, that's a good thing, of x, and it has to be with regards or with respect to x this time, so dx, and then hit enter, and look, we have the same answer. I did promise you a demonstration of the CAS capabilities of this calculator, so if you wanted to actually take this antiderivative, and I'll just copy this one back up here, you do not actually need the endpoints here. And so you can get rid of these endpoints only on a CAS calculator. Try it on your non-CAS one and see what happens. It'll just tell you it's an error. If I hit enter, look at that. It actually goes through and it gives me the antiderivative of this function. Now, I'm not actually a fan of the antiderivative the way that they wrote this here. It's weird that they didn't actually use an e to some power, but it does give you the antiderivative. Notice there's a variable in my answer up here. So either way, very powerful if you wanted to check your antiderivative. If you were doing it by hand, you could plug it in. It would give you that antiderivative. All right, let's jump over to the 84. Similar idea. If you are on our home screen here, most of your functions live in math. And then we're going to go down. It's right next to the numerical derivative, right? It says function integration. Hit enter as long as your calculator is updated. We just go from 0 to 6. Your E button lives above natural log because they undo each other, so second E, and then it was the negative 0.13. You can use X or whatever sounds good, and don't forget that there's a negative 45 out front, which I forgot. Notice I did second insert so I could type this in without deleting the rest. I don't even think it was negative 45, was it? Probably should have just looked at this. It is just plain old 45. Go me. And then we go to the end of this and we say dx. Great. There we go. And we found the same answer. As before too, you could have typed this into your graphing screen of your calculator. So then on the home screen, you could go math and then, what was it, 9? There we go. Yeah, math 9. 0 up to 6, and then instead of typing in the equation, since it's already in y1, we can use our shortcut over here, y1 of dx, and then enter. Look, same thing again. And the very last one, if you would ever like it, is on Desmos. And Desmos can also do integrals. It only does definite integrals. It's not a CAS calculator here, but we can go through. And if you want to do it, I know it's kind of harder to see with my keyboard, so I'll just do the ABC. You can type in INT, and it will automatically give you an integral from 0 to 6. And then same thing. You can just use plain old E on your keyboard. Desmos knows what's going on if you do that. And then we have dt at the end, and we get that same integral. So a whole bunch of different ways to do that. This is actually the fourth and final function you're expected to be able to use on your calculator. And you're like, well, why do I have to do that? Why don't I just do the antiderivative? Well, that's great, but what if we gave you a function where you don't know the antiderivative? And there are many integrals which you will not be able to find the antiderivative, and so you will have to use your calculator to get an approximation. You're like, well, but wait, if I don't know the antiderivative, how does my calculator do it? And the answer is through rectangles. Yeah, it actually goes through it, graphs your function, and then it subdivides it into itty bitty little rectangles, and it calculates the answer to all the rectangles. Now, these modern days and times, I'm sure there are many antiderivatives built in that they just plug it into, but at its core, yeah, it literally goes through it, draws rectangles, and it finds an approximation. And it can do that with any function as long as it can graph it, and your graphing calculator, I think, can graph just about any function you're ever going to be asked about. All right, so we have 2 problems left. Let's go ahead and see how you guys are doing on this. So here comes problem 2. I'd like you to try both A and B, and then we'll go through and see how you did. Ready, set, go. And you guys are back. Explain the meaning of the integral from 0 to 24 of P of t times dt. Well, let's start with P of t. P of t is units. It's in units of gallons per hour. And dt is in hours. And when you multiply those together, we're going to get a final answer of gallons. So if this is the rate that fuel is pumped from an underground tank, then, and we're going on for a certain number of hours, then I would say, and I always list the starting and the ending time values, so from t equals 0 to t equals 24 hours, the integral 0 to 24, P of t dt will give the total, because this sums things up, right? The total, that was supposed to be a t, but apparently my pen didn't cooperate, amount, see there's that amount again, of fuel pumped from the underground tank. Easy. Looking at units gives you a very clear picture. Fuel in gallons, I should probably say. All right, use a left Riemann sum with 6 subintervals to approximate the total amount of money earned. We always start with an integral. Integral 0 to 24, P of t times dt will give us a final unit of gallons. And we're going to go through and take a look at this. Now we should look at the base first. It looks to me like the base is always going to be a width of 4. And is that 6 subintervals? 1, 2, 3, 4, 5, 6, yeah, 6 subintervals. Cool. So I'm going to factor out that 4 ahead of time, and in particular realize that that's 4 hours times left Riemann sum, which means we are going to exclude the right one, and so it just becomes 250 plus all these fun things here. Don't forget to get credit for a Riemann sum. You need to show both a product and a sum. So don't go through and add all these up first and put that in there, because then there is just a product. We need to show a product and a sum. And this, by the way, will have units of gallons per hour. Great. From here, you can totally use your calculator to add all those up. You can try some mental math too. I think the mental math isn't too bad though, right? Because these are the only ones with 50s. We can add those. So that's 8. That's going to be 900, right? 900, 1100, 1600, 2000. I'm looking at 2300. And I'm sure you guys will let me know if I did it wrong, but I'm going with 2300. And if I did it wrong, it doesn't really change the problem. You guys can take it over from there. And so, oops, I should be using approximately here. They're pretty sticklers on that. And so we end up, oh wait, this is gallons per hour. Whew, words are tough today. There we go. The hours will cancel, and we get 4 times all of that. 0, 0. 4 times 3 is 12. Carry the 1. 4 times 8 is 9. And so we get 9,200 gallons. So are we done? Oh, wait. They asked us to approximate the total amount of money earned. We just found the total number of gallons. How do we continue that out? Oh, the fuel costs $3.50 per gallon. Silly us. So to find the amount of money earned then, I think we have to take 9,200, I'm just like leaving off one number all over the place, 9,200 gallons times, and this is more units, isn't it? $3.50 per gallon. So this one's kind of weird. So I'm actually going to write the word dollars at the end, per gallon, so that we can see that there. Gallons cancel. And as we go through, you take half of that, which I don't want to do this anymore, 9,200 times 350. We'll just do it right here. Okay, so we'll clear this out. So we have 9,200 times 350. We get 32,200. Awesome. So 32,200, and we're set. All right, last one. This one's somewhat local since I'm based out of Nevada. So to create hydroelectric power, water is released each day through the Hoover Dam. And that's funny. I wonder if my auto-corrected here. It's like that joke, right? What did the fish say when he swam into the wall? Dam! Yeah, but either way. Okay, so we're going to try to spell dam correctly. It's in Boulder City, right, just outside of Las Vegas. The Bureau of Reclamation recorded the following data for July 30th, 2010. We have a time t and then the flow capital F of t. Capital F of t is measured in millions of cubic feet per hour. Alrighty, use a left Riemann sum to estimate this and then interpret your results. I always start with the units. So capital F of t is millions of cubic, we know how to abbreviate that, of cubic feet per minute. And then dt, the time, is measured in cubic feet per hour. Awkward. And then dt is going to be in hours. So those will cancel, and those are just going to give us millions of cubic feet. All right, left Riemann sum, here we go. Start with the integral. We are approximating from 8 to 17, capital F of t dt. And notice we're just going from 8 to 17 here. That could throw some people off. They might include 6 and 19. And let's look for our bases. I don't think they're all the same here. So we have a base of 2, 1, 3, and 2. All right, and then we have a left Riemann sum, so we're going to exclude the last height. So we might as well just write all these out. So we have 36.7 is the height, and then the first base was a base of 2 up here, right? Okay, so there's 1. And the next one is going to be a base of 2. We already took care of that. And a height of 53.3, base of 2. Next one is going to be a base of 1 and a height of 87.7. Next one is a base of 3 and a height of 111.1. And then this last one is going to be a base of 1 and a height of 130.6. Again, you can graph this if you'd like, but you're really going to find yourself in a happier place if you can write these out and somewhat visualize what's happening. And we're going to go through and find that value, and I really don't want to. So I am going to say that this is going to be some number, and in particular, it's going to be in millions of cubic feet. Not per hour anymore, right? Millions of cubic feet of what? Of water are released from, and again, I'm just lazy, I say from t equals 8 to t equals 17. Easy. So this Riemann sum, again, gives us this accumulation, this total amount added up from 8 to 17, versus part C here, which should probably say part B, says estimate f prime of 10. This is saying at a specific moment, what is the value of f prime? But of course, you'll come back up here and you'll say, well, we have 10 right here, so what do we do? Well, if we're going to estimate f prime of 10, I always take the closest values above and below. So I'm going to take 8 and 12, and we essentially apply our mean value theorem without actually using the mean value theorem. And we're going to use these guys over here. So we're going to find f of 12 minus f of 8 divided by 12 minus 8. And again, this is the slope formula, the average rate of change formula applied to capital F. So this is going to guarantee something about capital F prime. Couldn't you write lowercase f? Yes, you could. So as we go through here, and we should also probably say that we are approximating f prime of 10. Show the setup. What are we trying to accomplish? F of 12 is 87.7, and f of 8 is 36.7. Oh, that actually makes the math much nicer. Over 12 minus 8, which is 4. Right? These 7s are going to cancel out. And then 87 minus 36. Oh, tough math. That's a 1. That's 51 over 4. Cool. And I'm not going to reduce because I'm a rebel. Show the computation that leads to your answer. You need to show a difference quotient like I did right there. It has a difference and a quotient. And then use the correct units. Well, capital F was on top of my difference quotient. And capital F has units of millions of cubic feet per hour. And then lowercase, or no, rather this is our time on the bottom. That's lowercase t, isn't it? And it said time is in hours. There we go. But then it said to explain the meaning, and this is not enough of an explanation of the meaning. So how do we explain this? At t equals 10, derivatives measure an instantaneous rate of change at one specific time. So at t equals 10, what's changing? Well, how do we say this? So this is the derivative of capital F, so it measures the rate of change of capital F. So we could say f of t is changing at 51/4 millions of cubic feet per hour, and that'd be fine. If you really wanted to think about that interpretation, what it means is, since this is positive, f of t is increasing every 4 hours at a rate of 51 million cubic feet per hour. And that's that. We're going to work on these interpretations over the next week and a half or so. Really, that's our main focus for these units of integration, these applications of integration. But this is a nice introduction to everything. Nothing too crazy went on. We got some calculator information. We got to work with the wild printer and talk about A equals R times T. So thank you for tuning in, and I'm very excited to have you back next class when we start working our way through a couple types of free response questions that you will see on the exam.